video is going to serve as a quick introduction to the properties of 45, 45, 90, and 30, 60, 90 triangles. So we're going to discover what the relationship is for each of them. So the first one we're going to start with is a 45, 45, 90 triangle. So in these three figures, we have squares with a diagonal drawn in. So the diagonal is bisecting the other right angles into a 45, 45, 90. So we're going to focus on just the triangle for now. And we want to figure out what's the length of that diagonal. So right now, we know if there are two sides of the triangle, we can do Pythagorean theorem to get the third side. So if we are looking for the hypotenuse across from the right angle, we would have x squared equals 1 squared plus 1 squared. So that would get us x squared equals 2. So I can take the square to both sides, so x equals root 2. Now I'm going to put a 1 in front of here because I know I have no coefficient, but that'll be important later. So we have 1 root 2. In the next triangle, when I go to look for the hypotenuse, I would have x squared equals 2 squared plus 2 squared. So we get x squared equals 8. When I take the square root, I get x equals the square root of 8, which simplifies to 2 root 2. In our third triangle, we have two sides that are 3, and we're looking for the hypotenuse again. So we have x squared equals 3 squared plus 3 squared. X squared equals 18. Take the square root, we get x equals the square root of 18, which is equal to 3 root 2. So if we look at these three figures, we notice that there's a pattern. They have two legs that are the same length, and the hypotenuse is the length of the leg with a root 2 added to the end of it. So our relationship in a 45, 45, 90 triangle is that we're going to have two congruent legs, which we can call length of L, and our hypotenuse is going to have a length of L root 2. Now let's switch and look at a different type of triangle. Let's look at the 30, 60, 90 triangles. Let's switch gears now and look at what happens when we have an equilateral triangle with an altitude drawn in. So when we have the altitude drawn in, it creates that right angle and splits the 60-degree angle at the top into 30. It also takes this side of the triangle then and splits it in half. So now I know that if I focus on just half of my triangle that has the right angle, I can use Pythagorean theorem to get that third side. So we would have 2 squared equals x squared plus 1 squared, which would get us 4 equals x squared plus 1. X squared equals 3, so x is the square root of 3. So I'll say this is 1 root 3. In the next triangle, we have sides that are 6, 6, and 6. So again, it's split that base into 3 and 3. So if I focus on my triangle, I have 6 squared equals x squared plus 3 squared. 36 equals x squared plus 9. We can subtract 9 from both sides. 27 equals x squared. X equals the square root of 27, which simplifies to 3 root 3. In the last triangle, we have sides that are 12, 12, and 12. So we can split that base of 12 into 6 and 6. So we would have 12 squared equals x squared plus 6 squared. 144 equals x squared plus 36. Subtract 36 from both sides, we get 108. So x is the square root of 108, which simplifies to 6 root 3. So in this type of triangle, there's three different angle measurements. There's a 30, 60, 90. So there's going to be three different side lengths. So we have our hypotenuse, which is going to be the longest side. Half of that is going to be the side across from the 30-degree angle. And across from the 60, we take that smallest side and multiply by a root 3. So the relationship in a 30, 60, 90 triangle is across from the 30-degree angle is the shortest side, which we would call S. Across from the 60 side is going to be S root 3. And across from the 90-degree angle is going to be 2S. Now, these special right triangles will help us because unlike Pythagorean theorem, I only need to know one of the sides in order to use the relationships to find the other sides, which we will work with in class tomorrow.